Hello everyone. In this control engineering and control theory tutorial, we explain how to linearize nonlinear models of dynamical systems in Simulink. This is the first part of the tutorial where we mainly focus on the relatively simple dynamical systems in order to demonstrate the general idea of linearization in Simulink. In our subsequent tutorials, we will explain how to linearize multiple input, multiple output systems and more complex nonlinear systems. In this tutorial, you will learn how to analytically linearize simple nonlinear dynamical systems. Then you will learn how to model nonlinear systems in Simulink. Then you will learn how to linearize nonlinear systems in Simulink. And finally, you will learn how to export linearized models to MATLAB Workspace and how to verify the linearization procedure. That is, in this tutorial, we give a relatively simple example and go through all the steps. First of all, how to analytically linearize by using Jacobians and partial derivatives, and we will guide you through the process of modeling Simulink and the process of linearizing the model in Simulink. Finally, we will verify the linearization procedure. Okay, first we explain how to analytically linearize nonlinear systems. As a test case, we will be using this nonlinear system. X dot, where dot is the first derivative, is equal to minus x multiplying sine of x plus the control input u. For simplicity, in this tutorial, we consider a one-dimensional nonlinear system and we assume that this system linearly depends on the input u. Of course, everything explained in this video tutorial can be generalized to more complex nonlinear systems. First, let's explain what is linearization and how we linearize dynamical systems. This dynamics can be written in this general mathematical form. And then the linearization procedure is, number one, first of all, we need to select the linearization point. The linearization point consists of a properly chosen state and a properly chosen input around which we will linearize this nonlinear dynamics. Then, the next step is to compute the state and input Jacobian matrices and evaluate them at the linearization point. These Jacobian matrices are actually the matrices of partial derivatives of f with respect to the entries of the state vector and f with respect to the entries of the input vector. In our case, everything will be scalar and consequently these df over dx and df over du will simply be partial derivatives of this equation. After we compute these partial derivatives, which are called Jacobian matrices, we will evaluate them at the linearization point. That is, we will evaluate this Jacobian matrix at x star, and we will evaluate this Jacobian matrix at u star. These are the standard A and B matrices of the linear model. After that, we can write the linearized model that has the standard form. Now, notice what's happening over here. Over here, we introduced the linearized state, x bar, and the linearized input, u bar. The linearized state is simply the difference between the state of this linear system, nonlinear system actually, to repeat, x bar is the difference between the state of the original nonlinear system and the linearization state. Similarly, u bar is the difference between the input of the original nonlinear system and the linearization input. After we form these relative state and input variables, we can write the state space model that looks like this, where A and B are these matrices over here. From this state space model, you can compute the transfer function relatively easily. Let us now apply this procedure. The first step is to select the linearization point. In my case, the linearization point is, the state will be x star pi over 2 and the input will be u star equal to 0. Next, let's compute the Jacobian matrix. Notice that this is f of state and input. Okay, the matrix A is simply the partial derivative of f with respect to x and evaluated at x is equal to, or actually, yes, x is equal to x star. Okay, first of all, let's compute df over dx. Let's do it over here. Df over dx is obviously, let's see, minus sine x minus x, and the first derivative of sine is cosine x. What is the partial derivative of u with respect to x? It's equal to 0. And consequently, this is df over dx. Then we need to evaluate this expression for x is equal to x star, or better to say x is equal to pi over 2. So let's do that. df over dx, where x is equal to pi over 2. And this is, let's write it nicely, minus sine pi over 2 minus pi over 2 cosine of pi over 2. Let's evaluate this expression. Sine of pi over 2 is obviously 1, and this is equal to minus 1 over here. Over here we have cosine of pi over 2, that's 0, multiplying minus pi over 2, that's simply minus 0. Consequently, this expression is minus 1. That is our a, which is actually a scalar in this case, is simply minus 1. Let's compute b. b is equal to partial derivative of f with respect to input evaluated at u is equal to u star, where u star is the input from the linearization point. Let's see what's happening over here. Partial derivative of f with respect to u, this part is 0, and partial derivative of f with respect to u is simply 1. Consequently, our B matrix is equal to 1. Here's B, and here's A. Okay, now our linearized state space model, which is only a single state equation, will look like this. First of all, we introduce the linearized state. The linearized state is actually the difference between the state of the original system, that is the difference between x and the state linearization point. Similarly, u star is the difference between u and the linearization input. The linearized state space model will have the following form. X bar dot is equal to a x bar plus b u bar, and by substituting the values for a and b, we obtain the linearized model that looks like this. X bar dot is equal to minus x bar plus u bar, and that's it. This is our linearized model. Here's the summary. This is our original nonlinear model, and this is the linearized model, where x bar is x minus x star and u bar is u minus u star. Next, let's derive a transfer function from this state space model. How to do that? Well, this state space model is linear and one-dimensional, and we can simply apply the Laplace transform to derive the transfer function. Note when applying the Laplace transform that we simply neglect the initial conditions, since the Laplace transform for transfer functions, or better to say the transfer functions, are derived and defined for zero initial conditions. Consequently, we type Laplace transform of x bar dot is equal to Laplace transform of the right hand side. We have here minus x bar plus u bar. Since the Laplace transform is a linear operator, we have minus Laplace transform of x bar plus Laplace transform of u bar. Next, let's define the Laplace transform of x bar as Laplace transform of x bar will simply be capital X with a bar of s, and the Laplace transform of u bar will simply be, or better to say, will simply be denoted by u bar of s. If we now substitute these values over here, we obtain x bar of s, let's write it nicely, multiplying s, that's precisely the Laplace transform of this term, and of course we have the initial condition in the time domain is equal to minus x bar of s, that's the Laplace transform over here, plus u bar of s. Now, since the transfer functions are defined for zero initial conditions, the initial condition can be neglected, and we obtain the following: s x bar of s is equal to minus x bar of s plus u bar of s. From this equation, we have that s x bar of s plus x bar of s, I simply move this term to the left hand side, is equal to u bar of s. And consequently, from this equation, we have that s plus 1 x bar of s is equal to u bar of s. That is our transfer function relating the inputs and outputs. In our case, the output is simply the state is x bar of s over u bar of s is equal to 1 over s plus 1. And this is w of s, representing the transfer function of our system. The next question is how to do the same procedure in Simulink. That is, how to model the system in Simulink, and how to linearize the system in Simulink, and how to export the linearized state space model to the MATLAB workspace. We will actually compare the linearized Simulink model with our transfer function derived over here. In that sense, and by using that strategy, we will be able to make sure that the Simulink is doing the correct thing. This is my advice to everyone. Always do a small example, always do a test example to test any software, any black box software that's used for control or for some other application. Okay, let's start with modeling. The first step is to open MATLAB and to start Simulink. We do that by typing in the command window Simulink. Then click on the blank model to create a completely blank model. The first step will be to model our original nonlinear system. And here, for clarity and for brevity, and such that I don't need to switch between two screens, I will write my original nonlinear model. The original nonlinear model looks like this. X dot is minus x sine x plus u. Okay, let's continue with Simulink modeling. From this equation over here, we can see that x is actually an integral of everything that's on the right hand side. That is an integral of x sine x plus u. The integration is performed with respect to time, dt. Let's model this system in Simulink. The first step is to model this integrator. So double click over here and search for an integrator. Here it is. Enlarge this block. Let's see what do we have here. The output of the integrator is x. We need x multiplying sine x with a negative sign. Okay, so the first step is actually to create a product. Double click here. We have a product. This will be x multiplying sinus x. That is, the output of this block is x sine x. The input is the first function that we multiply, that is x. And the second input should be sine x. Consequently, we need to create sine. Double click here and search for sine. Here it is. Connect this part and connect this. Good. Now this signal over here is sine x and this signal is x. This will be multiplication and we need to add the negative sign over here. The best strategy over here is to add a sum. That is, we will sum this term and this term. Now connect this part over here. However, this will be plus x sine x plus u coming from here. Consequently, over here you need to change and to replace plus by minus. Now we have that the input over here to this port of this summation block is minus x sine x plus u, or actually just minus x sine x. The u will come from this side. Let's create u. I will model u simply as a constant. Here it is. Then I will connect this part over here, and I will assume that u is equal to 1 over here. Okay, now we will simply connect this part over here to an integrator. That is, the output of this summation block is minus x sine x plus u, where u will be simply 1. Let's run this simulation. To run the simulation, over here adjust the simulation time, for example 20, and click over here to run the simulation. And over here nothing happens. You cannot see the results since you don't have a plotter or a scope. Double click over here and search for scope. Here it is. Connect the scope to actually the output of the system, that is to x, and let's run again and double click on scope. Here it is. This is our x as a function of time. Let's change this value over here, for example to 3, and click on apply. And let's run everything again. Double click on the scope, and here it is. We can see a quite nonlinear behavior of our system. By default, Simulink will linearize our nonlinear state space model with respect to the initial condition. And by setting the initial condition, we'll be able to set the point for linearization. To set the initial condition, we'll simply click here on the integrator and we'll put the initial condition. Over here, I want to simulate, or better to say, to linearize at the end my dynamics with respect to the state that's pi over 2. And I will set here the initial state to be pi over 2. Later on we will use this initial state for linearization. Again, to repeat, MATLAB by default, or better to say Simulink by default, linearizes nonlinear systems around initial states. And we can change this actually later on. However, due to the brevity of this tutorial and simplicity, we'll just use the basic settings. Okay, let's now run the simulation and let's see the output once more. Here it is. Good. We see that we start from approximately pi over 2. Next, let's learn how to linearize the system. To linearize this system, we need to specify the inputs and outputs for linearizations. That is, we will obtain a linearized state space model where the input will be defined by the user and the output will be defined by the user. How to do that? Well, over here, click on this line, double click, click linear analysis points and click on input perturbation. And then you will see this arrow over here. This means that we set the input for our linearization to be here. Okay, now we need to set the output for our linearization. The output for our linearization will actually be here. So select this line, do the right click, then linear analysis points and click on output measurements, and this will be the output. You will see that the output is automatically placed just after the integrator, and that's perfectly fine since this line coming out of the integrator is actually our x. Okay, let's continue. Now that we have input and output, click on apps, then over here search for model linearizer. Click over here and wait for a few seconds. Expand this. Now, let's explain what's happening over here. This is the standard option. This means that we are linearizing inputs and outputs. That is, we will derive a transfer function, or better to say even a state space model, where the inputs and outputs are actually defined by us. You can click over here to see what's actually defined. Now you have to be patient a little bit, and you can see constant and integrator, and this will be the input perturbation and the output measurement. Later on you can even define the inputs and outputs explicitly and you can call them. However, for simplicity and brevity of this tutorial, we will not play with that option. Then you see the operating point. The operating point is the model initial condition, and you can click over here to verify the model initial condition. Here it is. It's actually pi over 2. You can change it even over here if you want. Close this. And you have some other options over here. Now, to linearize this state space model, you can simply click on any of these icons over here, or you can simply click over here. However, I will simply click on body diagram, since it's also a good idea to see the body diagram. By clicking on the body diagram, you will see that over here you will obtain a linearized model. So click here and let's see the output. Wait a little bit. And you can see here that linearization results are being plotted, and here it is. Turn on the grid to see this. Good. And notice what happened over here. You can see your linearized model, and you can see that it's actually in a state space form. Double click on it, and you can see its structure. Here it is. We can immediately see A matrix. That's precisely our matrix A. Over here, it's -1. Then you can see B matrix is simply 1. B matrix is over here, it's 1. And C and D do not exist. Actually, C exists since the state is actually the output. However, D doesn't exist. Okay, and you can see the body diagram. Next, let's learn how to export this model to our MATLAB workspace and how to extract the transfer function for verification. So simply move linear system from here to here and drop the right click, and that's it. Now our linear system is in MATLAB workspace. Next, let's go back to the MATLAB workspace, click over here to open a new script, and let's go back to the command window and let's type whos. Over here we can see our linear system. Good. Let's just type linsys1 to see its structure. Here it is. Next, let's extract the transfer function from this linear system. To do that, you need to use the function tf. The function tf will define or extract a transfer function, and I will call the output as transfer function 1. Okay, here it is. And here it is. You can see that our transfer function is 1 over s plus 1, and that's precisely this transfer function over here. That is, we were able to verify that Simulink has properly linearized our model, and this is very important. Again, whenever you do something with Simulink, with MATLAB, with C++, or with any type of program that's usually a black box and that someone else wrote, always do a simple test, construct a system, and try to analytically compute the linearization, and then do the same thing in the software, and the results should match. Okay, that's all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thank you very much and have a nice day.